So last section of chapter 3, we're going to do section 5 here to kind of finish off chapter 3. So today we're going to talk about just an introduction to functions. We talked about equations quite a bit already. Functions are another way to kind of look at an equation. All functions can be written as equations. Equations aren't necessarily functions, but you can write functions as equations. So kind of keep that in mind. We're not going to do all of the objectives. We're not going to do the first one. We're not going to distinguish between dependent and independent. We'll talk about it a little bit, but really not going to be quizzed kind of over that piece of it today. We're going to define and identify relations and functions. How do we know if something's a relation? How do we know if it's a function? We're going to find the domain and range. We're going to identify functions by graphs and equations. And we're going to use what we call function notations to kind of help us evaluate functions. So quite a bit within this lesson. So let's get going. So just real quickly, you're not going to be really quizzed on this, or this isn't going to be part of your assignment, but we do need to be able to distinguish between independent and dependent variables. So we often describe one quality in terms of another. The amount of your paycheck, if you are paid hourly, depends on the number of hours you worked. So there's a dependent piece of it, and there's an independent piece of it. The cost of gas station depends on the number of gallons of gas you pumped in your car, the distance traveled by your car moving at a constant speed on the time traveled. These are all dependent and independent events. So if the value of the variable y depends on the value of a variable x, then we say y is the dependent variable and x is the independent variable. So with that being said, then, when we look at independent variables and dependent variables, according to our coordinate plane, our independent variable is going to be our x, and our dependent variable is going to be our y. Because the input that we put in there for x is going to, what y's result is dependent upon what we put in there for our x value. And that x value is going to change, and that y value then becomes dependent upon that. And you think about when we graph y equals 3x plus 4, we kind of always change that x value, and then that y value is going to change kind of in accordance to that. So there's two types of ordered pairs. We can have a relation. A relation is a set of ordered pairs, and that's what a relation is. It's just a set of ordered pairs. So 3, 5, 7, 8, 2, 1. That's an example of an ordered pair. A function is a little bit different than an ordered pair. A function is a relation. Okay, so all functions are just sets of ordered pairs, but for each first component of the ordered pair, there is exactly one value in the second component. Okay, so your x value essentially can't repeat in order for it to be a function. If your x value repeats, you no longer have a function. That first component can only happen once. If it happens more than once, then it is not a function. It's still a relation. It's a set of ordered pairs, but it's not a function because it occurred more than once. So if we look at this example, we've got the relation 0, 3, negative 1, 2, and negative 1, 3. We want to know if this defines as a function. Well, the answer is no, because if you look at the negative 1 here, negative 1 is repeated. So since negative 1 is repeated in two different sets of ordered pairs, then that relation is not a function. It's still a relation, but it's not a function because that x value is paired with different y values. So no, it's not an ordered pair because the first component ordered to the second. If we look at the second one, 5, 4, 6, 4, and 7, 4, and we want to know if that is a function or not. If you look at the x values are always changing. Since the x values are always changing, they're not repeated, then this is going to be a function. We don't care what happens to the second value or the y value. It's irrelevant. We only care about the x value. And since the x value doesn't repeat, then that is going to be a function. Okay? So that is a function. So this is what's called a mapping. A relation and functions can also be described in a correspondence or a mapping from one set to another. Anytime you've got a mapping of sets, you got to have all these kind of arrows going in between them. And as long as the arrow only goes to one spot, then you're going to have a function. So what they have described here is they essentially have the ordered pair described 1, 2, 2, 5, and 3, 6. Since that's what described in this, then this is going to be a function. We can just rewrite this as ordered pairs. And since the input value, the x value, only goes to one output value, the y value, then we can say this is in fact going to be a function. Okay, so this is a function. In this case, notice that we have the ordered pairs 1, 2, but then we also have the ordered pair 2, 2, and 2, 6. So 2 goes to two different spots. Since 2 goes to two different spots, then this is not a function because my input 2 goes to two different outputs, both 2 and 6. So that is an example of something that is not a function. So within functions, then we want to be able to find the domain and the range. The domain is going to be defined as all the values of your independent variable, or x. So your domain is all of your x values that are part of that function. And your range is all of the dependent variables, or your y values, that are part of that function. Now, it might be a set of ordered pairs, and you just list the x values as your domain and your y values as your ranges. It might be a graph, like we've done previously when we've talked about interval notation and all of those different types of things. So those different types of things happen as well. But remember, the domain is your input to your x values. Your range is your output, or your y values. So if we're asked to list the domain and the range of this relation for this table, and does it define as a function, again, we can write this as ordered pairs. We could write this as negative, or we could write this as 1,999 and 86,047. So we could write these as a set of ordered pairs if we wanted to. It doesn't really tell us we have to do that, but we just need to kind of give the domains. So the domains are going to be all of your x values. So when you're listing the domain, just D, which that's a beautiful D, by the way. For your domain, you're just going to list the x values. So our domain is 1999, 2000, ... the rest of them. Your range is going to be all of essentially your y values, or your subscribers in this case. So 86,047, 109,478, and so on and so forth. That's your range. Now, the second part of this says, does it describe a function? Does the input, the domain, ever repeat? Doesn't. So then this is going to be a function as well. Okay? So there's the domain, there's the range, they listed them all. And yeah, this is a function. Well, we could give domain and range for this as well. Domain is all of the x values that are going to be included in this function. This is a function, and we'll talk about why it's a function in a bit, but it also says it's a relation. But the domain is going to be all of your x values that can be included. So it's as far left as it goes and as far as right as it goes. So in this case, this graph is actually going down in this direction forever and ever and ever. So this graph is actually going from negative infinity all the way over to infinity, because it's not going to stop. So that's our domain for this one. Domain is all the x values that could be in this graph. And because those arrows are there, it's extending out in both directions forever and ever and ever. So that's our domain. Our range is how high and low this thing goes. And you always go from the lowest it goes to the highest it goes. So if we look at this graph, it's going down forever and ever and ever. So the lowest for our range that this is going to go is negative infinity. But it comes up and it stops. And it stops at a height of 4. So that's where our range stops, is at that height of 4. So our domain is how far it stretches out. Our range is how far it goes down to up. Okay? And you always start small to large. So in this case, we've got a domain from negative infinity to infinity, and a range from negative infinity to 4. Okay? So the arrows indicate that it extends forever and ever. So our domain is negative infinity, infinity. Our range is from negative infinity to 4. And notice it's a bracket there. It's a bracket there because that's kind of filled in. Since that's filled in, that's going to be a bracket with that. So that's domain and range when you're looking at kind of a piece of a graph. Kind of an agreement on domain, and this is kind of a general statement. Unless specified otherwise, the domain of a relation is assumed to be all real numbers that produce real numbers that substituted for an independent variable. So unless they give you certain ordered pairs, you're going to assume that a domain is all real numbers when we're looking at the things that we're looking at today. So we're able to identify if something is a function by looking at its ordered pairs or looking at its domain and range. And again, remember, if the domain repeats if the x value repeats, then it's not a function anymore. But you can also determine if a relation is a function by looking at a graph by using what we call the vertical line test. A vertical line test, if you draw a vertical line on a graph, and it intersects the graph in more than one spot, then it's not a function. If it intersects it in only one spot, then it's going to be a function. So if we look at these two things, if I draw a vertical line, and I got to be able to draw that vertical line anywhere. If I draw a vertical line anywhere on this first graph, okay, you'll notice that it only hits this graph in one spot. So therefore, since it only hits it in one spot, this is a function. If I do the other one and I draw a vertical line, you'll notice it hits there and there. Since it hits both of those spots, realistically what that means is that the point 1, -3 is on the graph and the point 1, 3 is on the graph. So my x value, that should be -1, but so that x value repeats. So that's what it makes it not a function. So this is not a function. And that's just called a vertical line test. And you can always do a vertical line test to determine if something's a function or not if you're given the graph. You can just draw those vertical lines, and they have to be able to be drawn everywhere. So if I have a function if I have, say, a graph that looks like, let's get rid of some of that. It's going to come back. So say that I have a graph that looks like this. If I draw a vertical line there, you can say, well, yeah, that's a function. But you have to be able to draw it everywhere. Now it hits there, there, and there. So it's not a function anymore. So this is not a function. The vertical line has to be able to be drawn everywhere. So that's the vertical line test. Right? Again, you can do the vertical line test to test if this one is. If you drew vertical lines in here, yeah, that relation is going to be a function as well. And now some other things that you could come across to determine if they're functions or not. And this is kind of how we're going to do these. My suggestion to you is anytime you get something that kind of looks like this, that you're not quite sure what the graph looks like, my suggestion to you is going to be to go to Desmos or find a graphing calculator and go into Desmos and type the equation into Desmos. And then we're going to just use the vertical line test. So this was 5x minus 6. Oops. I need to put a parenthesis there. Oops. Let's delete that. Delete. I need to get inside of there, and I'm going to put a parenthesis. 5x minus 6. Okay, so if we look at this graph, this is what this graph looks like in Desmos. If we do that vertical line test, notice that it never intersects it. So this is going to be a function. Okay, so yes, this is a function. If you look at the domain and the range for that, the domain, remember, is how far it goes left and right. The domain for this one, I don't know if it'll let me draw on this or not. Nope, it won't let me go. The domain goes from this point here off to infinity. So our domain for this is 1.2 to infinity. My range for this one, the lowest part that it has is 0 to infinity. So that's going to be the domain for that. So anytime you get something on your assignment today where they ask you to determine just by looking at it or just by giving you an equation if it's a function or not, go ahead, type it into Desmos and do it kind of in that type of situation. It's just going to be a little bit easier for us to do. So do those in that Desmos type situation. And again, we've got a couple more here that we could determine if they are functions or not. And again, I want you to do these by putting them inside of Desmos. A couple things, inequalities, no, aren't functions. It's not an equation anymore. It doesn't have an equal sign, so it's not a function. And the last one is going to be a yeah. Okay, the denominator is 0, but we just don't include it into the domain. Okay. So variations of a definition of a function. So a function is a relation in which for each value of the first component of the ordered pair, there is exactly one second component. A function is a set of distinct ordered pairs in which no first component is repeated, and a function or a rule corresponds to assigned exactly one range value and one range value to each domain value. So all of those essentially say that your x value can't repeat. If your x value repeats, it's not a function anymore. It's all of those things that they really say. Okay, so function notation. So function notation is anything in the form f of x is equal to. So a function f is defined by a rule for independent and dependent variables. We often use the notation y equals f of x, and you got to kind of always keep this in mind. I can replace a y value with an f of x if in fact it is a function. And this is called function notation. So the function notation is actually right here. That's function notation. So you can take an equation. In this case, if I have y equals 9x minus 5, that's an equation. If I rewrite it like this, f of x is equal to 9x minus 5. Now that's written as a function. Now, again, I said this kind of at the beginning of this. Functions can be rewritten as equations. Not all equations are functions. Like we kind of looked at that before in some of those previous examples. We had equations back there, but they weren't functions. But if I write something as a function, it is an equation. So I could solve it just like I was solving an equation by putting a y back in there for the f of x. And in our minds, a lot of times it's a lot easier to do. Instead of seeing f of x is equal to 9x plus 5, and I ask you to graph that, you're like, huh? If I tell you to graph y equals 9x minus 5, you say, oh yeah, I know how to do that. It's in slope-intercept form. This y-intercept is -5. The slope is 9 over 1. We can graph that pretty easy. Keep in mind that if it's a function, you can rewrite it as an equation. It's just a different notation so that we can denote that something is a function or not. Okay. Now, it is going to have an input, it's going to have an output, it's going to have all of those different types of things, just like it did before, but our input's still going to be our x value. Our output's just going to be now that f of x value, or y, when we're looking at functions. So again, keep in mind that those things are the same. That's the name of the function. The name of the independent variable is x. You'll notice the x approaches there, and then that's kind of the defining expression. So we can take these then, and we can evaluate functions. So let's say that we have the function f of x is equal to -3x plus 5 divided by 2. And we want to find the following. So essentially, we want to take that function f of x, and we want to evaluate that function for whatever is in our input value. So our input value here is x, but now our input value is going to be -3. So whatever that input value is, you are going to replace in the original function what the input value was. So in our original function here, x was our input. Now we want in that function -3 to be an input. So anywhere in that function that I see an x, I'm going to replace it with a -3. So it's kind of like substitution. That input value is going to be substituted in for what our original input value was. And then we can go ahead and solve it. So -3 times 3 is 9. 9 plus 5 is 14. 14 divided by 2 is 7. So we can say that f of negative 3 is equal to 7. Well, what does that mean? Essentially, that means that you've got the ordered pair. Your x value is negative 3. Your output is 7. Because remember, you can replace the f of x with y. Okay? You can replace the f of x with y. So we could have y equals, okay? And so on and so forth. Now, the key to this, and the key to functions always, is when you're evaluating functions, is to remember that whatever is inside of your function input, you're replacing it with whatever there. I can put a t there, I can put a smiley face there, I can put whatever I want there. So when it asks us to evaluate f of t, all we're really doing is substituting the x value with a t in this case. There's nothing left to do with that one. At this point, you're done. Okay? You can't simplify it anymore. You're done. I must use. I told you. Sorry. Excuse me. Bless me. It's snowing really bad right now. Sorry, you get to look. Snowflakes are huge right now. I mean, they're honking huge. They're like 2 inches in diameter. Sorry. Just looked outside when I noticed that. So anyway, so we can evaluate, different functions, and there's all of them evaluating their different functions and so on and so forth. So again, you got to kind of keep it in mind that if I have g of x is equal to 5x minus 1, and I'm asked to simplify g of m plus 2, this m plus 2 right here now is going to be my input instead of x. So I look at my original function, and now anywhere I see an x in there, I'm going to replace it with m plus 2. And make sure you write the rest of the stuff out, and if you have to simplify, that's 5m plus 10 minus 1, so that's 5m plus 9, and you're done. Okay, you've simplified it. It can't be simplified any more than that. Okay? And there's what it is. Okay? When you're looking at, if they ask you to evaluate f of 2 in this case, when you're just looking at a table, this is your x value. Okay. Your x value is 2. Go down, find your x value. Your x value is 2, so your answer for this one is 4. Your x value is 2, your answer for this one is 6. Don't overcomplicate these when you're doing these. Okay. If you're looking at a graph and they want you to find f of 2, your x value is 2, go over to your x value of 2, draw a line. There's your solution. Okay, there's your answer. Kind of always just kind of evaluating those by plugging in your 2's. So your answer there would be 3. So again, when you're finding the expressions for these, we're not really going to do this part, I don't believe. Let me look at the assignment real quick. We're looking domain, range, nope. Evaluating, we did that. Got one more type of question that we want to look at. Graphing, we're not going to worry about the graphing piece of it. But there is one more type of question that I want to look at. So let's go ahead and get into, like my home screen. Isn't that pretty? Let's get into OneNote. So the other type, one more type of question that I want to look at is I want to say, okay, what if we have, let's say we have 2 functions. Let's say we have the function f of x is equal to x plus 4, and we have a different function, g of x is equal to 2x. Now, what if I want to find f of 6 minus g of 6? And we want to find that type of thing. Okay, so we've got 2 functions now. We're going to do a function operation. We're going to take these 2 functions and we're going to evaluate them. So the first thing I'm going to do is I'm going to evaluate the f of 6. So I look in my f function, which is right there, and anywhere I see an x, I'm going to replace it with a 6. So f of 6 is going to equal 6 plus 4, or 10. So f of 6 is equal to 10, minus, now I'm going to find g of 6. Anywhere I see an x in the g function, I replace it with a 6. So that's 12. 10 minus 12 is negative 2, and that's your solution. Okay. So we can do these really on a couple different modes when we're doing these. Let's look at one more of those, and then we can get going on the assignment. So let's go g of x is equal to x squared minus 1, and f of x is equal to 7x plus 8. So we're going to find f of 2 plus g of 1. So f of 2, so I look at my f function, change the colors this time. So I look at my f function, I'm going to find f of 2. So that's 7 times 2 plus 8. 14 plus 8 is 22. So that's 22. G of 1. So that's 1 squared minus 1, which is 0. So my answer there is 22. So there's a brief introduction to functions. We're going to use those quite a bit in the upcoming chapters of things. Just remember when you're dealing with functions, domain and range. And the domain are your x values, your range are your y values. In order for it to be a function, your domain values can't repeat. Now you get one input to one output. If you have more than one, if you have a repeating input going to an output, more than one output, it's no longer a function. We've got that vertical line test that you can use, and then you got to evaluate them as well. A little bit longer of a video today. Apologize for that. That's just lots of information in this today. The assignment for today is about 13 questions. It's a little bit longer than they have been. Just take your time doing those, and you should be good to go. We will see you next time.